Water molecules form when hydrogen atoms bond with oxygen atoms, illustrating how simple elements fuse to create complex substances. Historically, thinkers like Maharishi Kunad and Greek philosophers acknowledged the existence of indivisible particles, reflecting a long-standing curiosity about the fundamental nature of matter. This philosophical pursuit of understanding atoms predates modern scientific methods, showcasing the evolution of ideas regarding matter's composition throughout history. According to the law of conservation of mass, mass cannot be created or destroyed during chemical reactions, establishing a cornerstone principle in chemistry. This critical law was formulated by scientists such as Lavoisier. John Dalton significantly advanced the concept of the atom, enhancing our comprehension of atomic theory and its broader implications. His contributions built upon earlier laws, paving the way for contemporary atomic science. Atoms unite to form molecules, which are vital components of matter. For instance, water, composed of 2 hydrogen atoms and 1 oxygen atom, exemplifies how elemental combinations yield diverse substances. Atoms are exceedingly small, with a radius of merely 300 picometers, illustrating their minuscule dimensions on a quantum scale. They are more than just indivisible units of matter. Protons and neutrons constitute the nucleus of an atom, with electrons orbiting around it, akin to planets circling the sun. This arrangement is vital for the stability of matter. Quarks and leptons are the fundamental particles that compose protons, neutrons, and electrons, revealing an even deeper layer of with electrons orbiting around it, akin to planets circling the sun. This arrangement is vital for the stability of matter. Quarks and leptons are the fundamental particles that compose protons, neutrons, and electrons, revealing an even deeper layer of complexity within the fabric of matter. These particles rank among the smallest known constituents. The Planck length represents a key concept in quantum physics, delineating the point where classical physics can no longer adequately describe particle behavior. This measure is far smaller than the tiniest atom. String theory introduces the idea that strings are even smaller than Planck particles, implying a more profound fundamental structure in the universe. Although this theory remains largely speculative, it holds promise for future exploration. The possibility of endlessly dividing particles prompts profound questions about the nature of reality and existence. This concept suggests an infinite complexity embedded within the universe, observable at both vast and microscopic scales. In nature. This process underscores the crucial role of atoms in forming larger compounds. In ancient India, Maharishi Kunad and Maharishi Katin made significant contributions to the understanding of atoms, proposing that all matter consists of indivisible particles. Their insights laid a strong foundation for further scientific exploration. Similarly, Greek philosophers like Democritus and Leucippus independently advanced the concept of the atom, showcasing the universal nature of this scientific idea. Their terminology and theories continue to shape modern scientific discourse. The 18th century marks a pivotal era in physics, primarily due to the foundational laws established by scientists like Lavoisier and Dalton. Their groundbreaking work set the stage for the development of modern chemistry. A comprehensive understanding of molecules and their compositions is crucial, particularly in the examples of water and carbon dioxide formation. These molecules are composed of specific combinations of atoms. Moreover, the structure of atoms reveals that they are predominantly empty space, challenging conventional ideas of solidity. This realization invites deeper inquiry into subatomic particles. Each atom is made up of 3 primary subatomic particles: electrons, protons, and neutrons, which together constitute the atom's architecture. Protons and neutrons are located in the nucleus, while electrons orbit around it. Diving deeper, quarks and leptons emerge as the fundamental particles that form protons, neutrons, and electrons. Quarks, astonishingly smaller than atoms, combine to create protons and neutrons. The 4 fundamental forces of nature, including gravitational and electromagnetic forces, play a pivotal role in maintaining the cohesion of atomic particles. These forces dictate the interactions of particles throughout the universe. To further comprehend these forces, fundamental particles like photons and gluons are essential. These cannot be subdivided any further, thus establishing the limits of classical physics. Moreover, the Planck length signifies an extraordinarily small scale within quantum physics, theorized to be even smaller than atoms and associated with singularities found in black holes. This concept challenges our perceptions of size and reality. In addition, string theory introduces the notion of entities smaller than Planck particles, proposing a deeper layer to the universe's framework. Although theoretical, this idea hints at exciting potential discoveries in the realm of physics.